So a goodness of fit test is going to be an inferential procedure that's used to determine whether or not a certain frequency distribution follows a specific distribution. What we're going to be doing is comparing what we expect under the assumption the data follows some specified distribution to what we actually observe. And so we have to learn how to get these expected counts. So let's say there are n independent trials of an experiment where there are at least 3 mutually exclusive possible outcomes. And that'll become clear when we see an example, what I mean by that. We're going to let P sub 1 represent probability of observing the first outcome, then capital E sub 1 will represent the expected count of that first outcome. P sub 2 is going to represent the probability of observing the second outcome, that should say. And E sub 2 represents the expected count of the second outcome, and so on. So the expected counts is nothing more than n times P for each corresponding probability. You'll recall the expected value of a binomial random variable is n times P, so this is just an extension of that idea. So let's look at an example. For any number representing a positive count, the first digit cannot be 0. In other words, when you write a number like, say, 12, you wouldn't write that 0, 1, 2, right? And so the first digit of any number is always going to be a non-zero value, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So you might think that the first digit of numbers might all be equally likely, right? So you're just as likely to have a first digit that's 1 as 6 as 9. But Benford's law states that in many situations where counts accumulate over time, the first digit in the count follows a pattern. So if you went to Bloomberg's website, it gives information on the stock price and trading volume of members of something called the S&P 500 stock index. So this is just a bundle of 500 different publicly traded companies. So like, for example, Walt Disney is in the S&P 500, Amazon is in the S&P 500. A random sample of 100 stocks was selected and the first digit of daily stock volume was recorded. Daily stock volume is how many shares of a particular company trade on any given day. So that's the volume of a stock. To get some intuition on Benford's law, suppose 100,000 shares of a particular stock have been traded on the first part of a business day. To reach the 200,000 mark, it will take approximately a 100% increase in time. To go from 2 to 300,000 shares, we require a 50% increase in time. After that, increasing from 3 to 400,000 is a 33% increase in time, etc. So in these settings, the common first digit is 1. The next most common first digit is 2, and so on. And the least frequently occurring first digit is 9. So the relative frequencies of the first digit, according to Benford's law, are shown right here. Okay, this is Benford's law. So first digits occur with a relative frequency of about 0.301. The first digit 2 occurs with a relative frequency of about 0.176, and so on. We're going to determine the expected counts for each first digit, assuming the first digits follow Benford's law. And so first and foremost, what you want to do here is recognize that our sample size is 100. So n is 100. So if we want to know the expected count of the first digit being 1, that would be n times the relative frequency of observing a first digit of 1 according to Benford's law. So this is going to be a 100 times 0.301, which is 30.1. The expected count of the first digit being 2 would be n times the relative frequency of observing a first digit of 2 according to Benford's law. So that's going to be 100 times 0.176, and that gives me 17.6. And we could do this for all of these different first digits. So if I wanted the expected count for the first digit being 9, that would be n times the relative frequency of observing a 9. So that would be 100 times 0.046, which is 4.6. And so that's all there is to it for finding expected counts.
So the relative frequencies are set in stone.
The relative frequencies are based on some known probability distribution.